So anybody have any questions on what we're going to do or what we've been doing? So the rest is, I'll lecture today and tomorrow, and next week I will lecture Monday, Thursday, and Friday, and Dr. Belmar will do Tuesday and Wednesday. No questions, huh? Okay, well, if you don't have any questions, I'll start rambling. Okay, we've been talking about pressure bonding or cold weld. I've been calling it cold welding, but it's really variations in pressure bonding. And if you want to think about it in terms of some sort of one-dimensional diagram, you'll later learn that I love one-dimensional diagrams, mostly because I can follow it myself. But I also like one-dimensional diagrams on a log scale. If I have 1 megapascal of mechanical pressure, what's 1 megapascal in PSI? Some units that make any sense to us. 145 PSI, okay? So 145, down in this region, plus or minus a little bit of one megapascal, that's where you're just fixturing two parts, okay? I mean, if I stick a 1 pound weight on the table and it's 1 square inch, that's 1 PSI, and it just sits there, right? That's sort of fixturing. Diffusion bonding you can do at 100 megapascals of pressure, which is about 14,000, or yeah, 14,000 PSI. You can do diffusion bonding. You will find that there's a liquid phase diffusion bonding that's somewhere down in here, almost in the fixturing pressure. But cold welding in general, if I'm just sliding two surfaces together, I've got to get up to even higher local pressures. And explosive bonding, you're getting up to lots of megapascals, okay? You're essentially getting impact loads to deform these things. And remember, the two things, you got to get rid of surface contamination, you got to get rid of surface roughness. So what we're doing is we're going to try to get something that breaks down by shear these interfaces, these little mountain peaks. And I showed you this before, I'm pretty sure, which is a ultrasonic welding wedge bond. This is a little gold wire or whatever. Actually, it's aluminum silicon wire on an aluminum substrate. So it's maybe not for microelectronics, but lighten that up a little bit. So I think I showed you this before, but basically you had a wire, and right in the center here, you just have a normal force squeezing on this, and you don't get the real bonding until you actually get shearing and break down those surface asperities and extrude out the impurities. Now, another thing, we talked about friction welding, and this is, someday they're going to make one of these things that automatically gets the right lighting. This actually is a linear friction weld between steel and copper. Steel and copper don't like to mix very well in the solid state. So you can make a dissimilar metal joint, and you can see the difference in mechanical properties here, and actually up here you can see you transferred a little bit of steel and you kind of broke the bond and stuff as you're going along. There's another process called linear friction welding. Not linear friction welding, but friction welding. Not linear friction welding, but friction stir welding. Where'd my friction stir weld go? Oh, it's right here. So friction stir welding was the most recently invented welding process from about 25 years ago or so at the British Welding Institute. Some guy who was studying friction welding decided how can I vary the geometry? And he just took a milling machine and he put a steel bar in it, and he essentially ran it through, actually he may have started with a molybdenum bar so far as that goes, but he ran it spinning it around, and he ran it between two plates. And here is a linear friction stir weld, I mean, where you came across, that's the bottom, the top. They always machine off the top because it looks terrible. Okay, you're basically stirring and breaking the weld as you go, but you generate enough heat that you're forging the whole thing together as you're going. Okay, and if you do it properly, you can get good bonds. You'll see there's no distortion in that. One of the big problems with aluminum, because it has a 6% volume change on solidification, One of the big problems with aluminum is it will tend to distort on you much more severely than steel. Steel's like 2.5%. So aluminum, even though it's lower melting, tremendous distortion problems when you fusion weld. And so, boy, when this came along, NASA, that's made by NASA. One of the students gave it to me. He'd worked at NASA. They were pushing it. Boeing spent $10 million on a friction stir welding machine for some aircraft wing component attachments. You have to have big, heavy fixturing because you're basically just forging things under very high pressure. And you're also spinning. And there's been a lot of research done on friction stir welding in the last 20 years, partly because it is a new process. I had mentioned explosive bonding at the end last time and mentioned how it was sort of discovered back in the days of World War II. They found that some plates were there, you know, someone shot at a ship or shot at a tank, and when everything was all done, things that, big flat surfaces that had not been bonded were all of a sudden stuck together. And basically you start with a base plate. This might be 4 or 5 inch thick steel is a typical application where you're going to make a clad vessel because you can't afford to use all tantalum for, let's say you're going to make concentrated sulfuric acid in a chemical plant, or your process uses concentrated sulfuric acid. All the gasoline we make, it basically is made using sulfuric acid, concentrated sulfuric acid as a catalyst. There are only 2 materials that you can use to hold concentrated sulfuric acid. One's graphite, and they make graphite vessels for concentrated sulfuric acid. What's the problem with the graphite pressure vessel? Graphite's sort of brittle, okay? And when the thing goes boom and it's full of sulfuric acid, it's not a good day, okay? Tantalum is the other material, and tantalum is great, except it costs about the same price as silver, okay? So you tend not to like to use tantalum, at least 100% tantalum, but you don't need very much tantalum. It's completely resistant to the sulfuric acid. So you basically would take a tantalum plate and a base plate, clean both of the surfaces, and then you'll have a little buffer plate in here, an explosive, and you basically lay it down against the anvil down here. Usually the anvil is something like some granite mountain, okay? Nothing very sophisticated here. They may put a great big steel plate on top of a granite mountain, okay, but nonetheless, and they do it at a certain angle, and these angles tend to be 10 to 15 degrees, depending on the material. They detonate it, and an explosive doesn't just kind of go boom all at once. It actually burns from one end to the other. If you have a high-speed camera, you can see it burning. It just burns very fast. And it basically just pushes this thing down. Here's the burning velocity of the detonation, and you create a little shock wave in here, and the shock wave will produce a little interface like this. You actually get enough high pressure, you actually create a jet. And people have modeled this. I don't know if they've ever taken high-speed movies, but you actually are breaking up that surface right at the impact angle point, and you actually get a jet, and you are creating new surface, and you're slamming it together so fast that it can't recontaminate. Now, is anybody, here's a nice pictorial view of the process out of the Welding Handbook, showing the burning and slamming down, and then you take the stuff and you flatten it and cut it and roll it, and you weld it up into a pressure vessel. Okay. Turns out the greatest use of the chemical that's used the most of all the inorganic chemicals. Yes.
I was just going to ask if the concentration or the detonation from concentration where it doesn't affect the base metal.
Doesn't affect the base metal because it's really just where these two things are coming together within like 3 or 4 thousandths of an inch. that you're disturbing the metal. If you start looking for how deeply you created new dislocations and change in the microstructure, it's 100 microns. The rest of the base material doesn't even know it. It's just a great big anvil. And you get that, actually, one way to think about it is, if you take the deformation processing version of this course or module in this course, if you just think of an indenter on a great big thick piece of steel, the indentation is only about, if this is 2R across, this will be about 4R across, okay? If you're doing a hardness test, the amount of material that you deform is about, goes out another distance from either side, okay? And it goes down about a similar distance. And so this whole deformation zone is probably only the size of a pencil lead, okay? It's a very, very thin layer where you're deforming the material. Does that answer your question? Okay, so I don't remember what I was saying before that, but it doesn't really matter. Another application is to make plates that you can bond aluminum and steel together. These are transition joints where you slammed aluminum against steel in an explosive bonding operation, then you cut it up. And this is one of the things the Navy does for all of their superstructures on their ships, where they go from the hull of the ship is made out of steel because it needs to be inexpensive and have good capability against people shooting at it and stuff. To the superstructure, the top of the ship is usually too heavy. You want lightweight or the ship will tip over in a storm and things. So they have a steel base plate. They put one of these transition joints in here. This one happens to be a 3-ply one, so you add carbon steel to aluminum, and you just fillet weld the steel to the aluminum with one of these transition plugs. The only problem you then have is you now put a galvanic couple of aluminum and iron into a seawater environment, and it corrodes. Okay, it corrodes just great. In fact, there are theories that there's disputes about this, but I told you about the Exocet missile that hit the Sheffield. This was before most of you were born, but those of us that were living in the early 80s remember the Argentinians decided to take over the Falkland Islands because they call them can't remember what their name for the Falkland Islands is. But the islands are off the coast of South America, across the off the coast of Argentina, and Argentina claims them, but the British have, from when the British Empire ruled the world and the sun's never set on the British Empire, they call them the Falklands, which is I guess, a Scottish name or something. And the Argentinians called them something else. Well, one time in the early 80s, the Argentinians decided that Britain was now a third world country and was so far away that they couldn't really fight a war with the Argentinians in the Argentinians' backyard. So they decided to invade the Falkland Islands and take them over. This is sort of the same thing that's going on between Taiwan and Korea and China and Japan and stuff over little islands. And these things get to be important because underneath these islands you have oil deposits and things, okay? So in any case, so the British decided they didn't like this, and so they went to war to get the Falklands back, and they ultimately were successful. But in the whole thing, the Argentinians fired an Exocet missile. Now, Exocet missiles are not that big, okay? I mean, I don't know that I could lift one, but they're probably within my wingspan. Anyway, it hit the British cruiser Sheffield. Now, a cruiser is a pretty big naval ship, and it wiped it out. Not because the Exocet missile wiped it out, but one of the theories is it set the aluminum on fire. Okay, aluminum burns really well. Magnesium, you know how well it burns because that's what most of the fireworks are. Some fireworks have aluminum in it, but magnesium powder and aluminum powder will burn like they're flares. That's the power for a flare. It's also the power for rocket motor fuel. Okay, they use metal powders, aluminum, magnesium. They give off tremendous heat of combustion. It's very hard to ignite aluminum, but it can be done. There's something we call thermite welding. Okay, and thermite welding has been around for ever since we had aluminum over 100 years ago, cheap source of aluminum. You take aluminum powder, you mix it with iron oxide, it just looks like sand. You take a blasting cap and you ignite it, and the aluminum will reduce the iron oxide to molten iron and aluminum oxide. Just a chemical reaction, exchange reaction. The aluminum steals the oxygen from the iron, leaves behind iron, plus a lot of heat. You get about 2,000 degrees centigrade out of this. And so they actually use this process of igniting aluminum to weld steel rails together. I went down to Roslindale once to watch this, okay, about 30 years ago. The MBTA was welding two train tracks together, and they basically, it's a very simple process. You take this mixture of aluminum and iron oxide, and you put it in this steel bucket that's lined with fire brick, and it's got a hole in the bottom, except at the hole it's just got a little piece of aluminum foil. Actually, maybe it's a 1/16 inch of aluminum, just a little aluminum sheet there. And you set everything up, and you put some molds around the two train tracks. So you got some ceramic molds that are contoured to fit the sides of the railroad rails. And you set this bucket up on top, put the mixture in of aluminum and iron oxide, set it off with a blasting cap, and stand back, because you got the 4th of July inside of there, and the sparks are flying 10 feet in every direction. Hopefully you don't burn down don't set fire to someone's lawn in Roslindale. And within 2 or 3 minutes, actually less than that, within 20 or 30 seconds, you probably have built up enough iron that it melts through that aluminum plug, because aluminum melts at a fairly low temperature, and all this molten iron just drops down. You make a little casting, and we call it a thermite weld. There are some people that believe that the World Trade Center didn't fail because the planes hit it, but because it's a government plot. They actually set off thermite reactions inside the World Trade Center and cut the beams in two and caused the whole thing to collapse. 18% of Americans apparently believe that the US government destroyed the World Trade Center. It's called the 9/11 conspiracy theory, okay? Has anyone ever seen any of this stuff? You've seen it, I know. None of the rest of you have seen it? I've heard of it because I'm the major foil. I wrote an article on the World Trade Center, why it collapsed. And it's not since last week, or maybe it was when I got back yesterday. There's something called 9/11 TV, and they sent me 2 DVDs, and they want me to watch their theory about how all this stuff happened. Because they look at the World Trade Center, they see all these sparks coming out. And they say, see, that's proof of a thermite reaction. You get lots of sparks. And I said, well, I don't know. When did they turn off the electricity on the building? Because if you have a fire in a building and 2 aluminum, or not aluminum, but 2 electrical conductors, with 4 megawatts of power, electrical power behind them, touch each other, you'll get a shower of sparks too. So all these things that they say are proof usually have another explanation, but nonetheless, I've been listening to this for years on the World Trade Center. Explosive welding has found a lot of niche applications. One of the things that people have to do is they build tube sheets, great big boilers. All the utilities have great big heat exchangers to generate electricity in their power plant. And in that they have a great big tube sheet. These could be 10-inch thick steel. They drill a bunch of holes that might be anywhere from 3/4 of an inch, 1 1/4 inch, and they put tubes in them. And one of these tube sheets could be the size of this room, big circular disc the size of the room, and 10-inch thick steel with 10,000 holes in it and all these pipes. And each one of those pipes might be a 100-foot long U-bend, okay, typically. And that's going to be one end of a great big heat exchanger. So you flow all this water through there, and you generate steam in your nuclear reactor or your coal-fired plant, and you transfer heat to make steam to go through your turbine to generate electricity. What each one of those 10,000 pipes going through the tube sheet. You have this big thick tube sheet, and you have a pipe, and you need to make a joint between the tube sheet and the pipe so you don't get water leaking out between these things. You also, if you don't get a good seal here, you get crevice corrosion in here over time, and I mean, one of these heat exchangers costs $50 million. Okay, they're not cheap, so you don't like to have them corrode on you. So one technique they use, they sometimes just do an arc weld up here, but that takes forever. Okay, to make 10,000 welds in the thing. But one thing that seals it very quickly, they just put a charge in here, and they taper the holes, and they essentially have the tube inside in here, and they have a detonation thing in here. They go slamming it against there. That's the proper angle of 10 or 15 degrees, and they slam it against there and make an explosion weld of the tube to the tube sheet. Because you can make an explosion weld without getting macroscopic shear to break down these asperities. On the microscopic 100 micron level, you actually are deforming that material and getting tremendous surface roughness and blowing that contamination out of there in these jets that form at the interface. So that's explosive welding, discovered in World War II, but now used for lots of other things. Any questions? Now, if you're going to do this pressure welding and there really are only about 6 orders of magnitude of pressure variation that we deal with in structural welding, from fixturing two pieces next to each other, to doing diffusion bonding, to doing cold welding, to do explosive welding. So there's only so many megapascals we're going to use in squeezing things together. You can shear these things and try to get rid of the asperities, but you have to get the metal-metal contact in enough time to keep from having all the air come back in to contaminate the surface. Does anyone know how long it takes for air to contaminate the surface? If I were to break a piece of chalk, how long did it take for that freshly formed surface to get contaminated by air and CO2 and moisture? And there's lots of oils in the air. Does anybody know why we have all these oils in the air? Trees give off oil, plants give off oils. They're sort of always raining a little bit of residue, okay? So you ever wonder why? Well, none of you are wearing glasses, but you know, I don't clean my glasses for 1 or 2 days and they just got this little oily film on them. There are all kinds of things that we're breathing all the time, okay? Contamination, if you will, in the air. Well, it turns out that there's a guy, Irving Langmuir. And Irving Langmuir won the Nobel Prize. He was working for General Electric. And Edison had invented the incandescent light bulb, but they didn't last very long, like less than 10 hours, which was getting kind of pricey to use. I mean, he started out, anybody know what material? He didn't use tungsten first to make the incandescent light bulb. He used carbonized horsehair, okay? So he would carbonize the hair, he'd end up with a graphite thing, and that didn't work very well, but they learned that tungsten would last, you know, I think the carbonized horsehair might last an hour or something before it would vaporize. Anyone ever break an incandescent light bulb? It goes pop, right? Anybody know why it goes pop? It's about a half an atmosphere of argon in there. And a half an atmosphere of argon, you don't want to make it a full atmosphere when it's cold, because when you turn the light bulb on, it'll be a positive pressure in there as the gas expands, and you don't want to crack your light bulb from internal pressure. So they put about a half an atmosphere of argon, and Langmuir in the early days was the one who figured out they initially were just pulling a vacuum to keep the tungsten from oxidizing. And Langmuir turned out to be a great surface scientist, and he studied the evaporation of metals and the evaporation of tungsten. And if you just evaporate tungsten into a vacuum, it will evaporate very quickly. But if you've got a half an atmosphere or an atmosphere of argon atoms, as that tungsten tries to evaporate, that tungsten atom is going to hit the argon atom, it's going to be pushed back down, and you can slow down your vaporization rate by a factor of 100. So if you made a tungsten light bulb with a tungsten filament that was in a vacuum, you might get a 10-hour life. If you do it with half an atmosphere of argon, you'll get a 1,000-hour life, okay? So Langmuir was a great surface scientist and won the Nobel Prize while working at General Electric Research. And they now have named the time to form a surface layer of contamination after Langmuir. So the Langmuir is equal to about 10 to the minus 8 atmosphere seconds. What this means is in 1 second, or at 1 atmosphere, it takes 10 to the minus 8 seconds to form a film of oxygen or water vapor or whatever's in the air. A monolayer of atoms will hit the surface in 10 to the minus 8 seconds. So if I want to stick these two pieces of chalk back together after I break them, I have to keep them in perfect registry because the roughness has to match up, right? If it's a brittle material, it should match up, but I better make sure I didn't change the angular orientation by even a millionth of a degree. And I also have to stick them back together within 10 to the minus 8 seconds, or less, okay? Now people have done this experiment, and I told you that under ultra high vacuum, they took gold surfaces, polished them, and stuck them together. But they had to be at something like 10 to the minus 12 atmospheres so they could create that surface and stick it back together, and they would have 10, 15, 20 seconds in order to stick it back together before they got contamination, okay? So in general, in most of the part of the world where we live, it's hard to stick things back together quickly enough, okay? But in fact, what's going on in these explosive bonds and things like that, you're not necessarily sticking it back together within 10 to the minus 8 seconds, but you'll have other materials in there, gases that get pushed out of the way that don't contaminate it and don't have very many layers, or they're not strongly absorbed or whatever, okay? So, but generally, you can't beat the speed of gas, okay? The Langmuir will usually kill you, okay, in terms of evaporation and stuff. I'm going to give you an example in a second where NASA found out in the very early days of the space program that when they were in ultra high vacuum that things didn't work. But it's important for us to learn something and think, or actually you've probably already learned it in some of your other courses. Remember, I'm actually trying to prove to you you actually knew some of these things, you just had to put them together. And I think I put this up before, and this is just the old graphite and diamond, and I brought it out at the end of one of the classes. And we have carbon atoms, 2 configurations, sp3 hybrid tetrahedral bonds, sp2 triangular bonds, forms a hexagonal close-packed crystal structure. Graphite diamond, okay? Very different properties because the bonding is different. In sp3, we have no free electrons. In sp2, we're going to have some free electrons. sp3, we got 4 orbitals, 2 electrons per orbital, stable octet. Here, we've only got 6, or three orbitals, 6 electrons are taken care of. I got another 2 electrons. There are bonds, but they're not localized bonds, and those electrons can go running around, typically on the basal planes, okay? Whereas here, those electrons, strong covalent bonds, not a lot of free electrons in here. And because there's no free electrons, it's transparent. Light goes right through it. There's no free electrons to absorb the light. Carbon is black. There's free electrons that absorb the light. Same thing with electrical conductivity and insulator. Because whether you have free electrons or not, there's a guy named Cattell, who was an MIT undergraduate physicist. I think he went somewhere else. But John Wolfe, who had my office back when I was a student, or I now have his office, however you want to say it. Cattell was an undergraduate here, and he wrote a book on solid-state physics that used to be used when I was a student studying materials. He once told John Wolfe told me the story, that if he knew the position of every electron in the solid, he could tell you all the properties of that material. In many cases, you don't really care what the ions are, okay, with the core, you know, whether it's iron or cobalt or whatever. Now, you care about them in the sense that they control where the electrons are, but it's actually the electrons that give you the properties, was Cattell's point, of the material. And you can see that if you just compare the properties and go down through this. I think you've got this in your notes. But I put a mechanical here is graphite is a lubricant, diamond is an abrasive. Now, diamond is an abrasive because it's hard, it's got this three-dimensional structure. Graphite's a lubricant. Why is graphite a lubricant? They're carbon-carbon bonds. It turns out NASA found out, to their chagrin, that graphite is a lubricant because these basal planes tend to be sites to absorb carbon dioxide and oxygen as a surface film layer. There's a certain surface energy associated with the basal plane. There's a surface energy associated with the diamond, but it's isotropic because of the crystal structure is symmetric. This is not symmetric. You have very anisotropic properties, and it turns out my atoms are getting out of line. Must be high temperatures, right? In any case, what happened is they used graphite as the lubricant in the early Mercury space shots when they went up into space, and they got down to very low pressures, like 10 to the minus 10 atmospheres. And at those pressures, you could strip the oxygen and the CO2 off the basal planes of the graphite. Now I have carbon-carbon bonds between the graphite particles, and those are very strong bonds, and all of a sudden it was like putting diamond powder in your journal that you're trying to that's supposed to be a lubricant. And the astronauts are up there, they're finding the knobs are sticking and all kinds of things are going wrong, which is why we tended to just send people up his little arc into the Atlantic. The Soviets, on the other hand, sent Yuri Gagarin up, and he got to take 3 trips around the Earth before he came down. They didn't care as much. You know, we sent up a dog first, I think, or maybe they sent up a dog first. But in any case, there's sort of a different value of safety and risk in the two cultures. Anyway, because of that, NASA got very interested in cold welding, and they actually started funding research. This is a reprint of a book, Adhesion or Cold Welding of Materials in Space Environments. And this was, when was this? This is like 1964 or something. Well, 1967, okay. Was when they held the conference, but they, after, what was, Alan Shepard was 1959 or something. Anyway, he was the first American in space. But, you know, so 8 years later, they're now having a conference to talk about how things stick together in space. And in fact, they do stick differently in a vacuum than they do with contaminated air. And out of that book is this handy little chart from that same ASTM special technical presentation. Here's the, you can look at the altitude in hundreds of thousands of feet. Here's Sputnik 1. Okay, here's pressure in millimeters of mercury, microns, density, mean free path in miles. This is miles between atoms. Okay, you can talk about 100 miles between atoms when you're up here in the apogee of Sputnik 1 or something for the mean free path. That's how far atoms go before they collide with another one. That's not how far apart they are. It's how far they go before they run into another one. Okay. Impingement rate, time to form a monolayer. Here's your good old Langmuir up here at sea level. It's somewhere around 10 to the minus 8, 10 to the minus 9 atmosphere seconds. So I'm pretty sure that's in your handout notes too. So it turns out that surface energy becomes important in all this cold welding how strongly bonded are the impurities to the surfaces, and we can get some feel for that by actually looking at some surface energies. So if I plot, I go to a book, this comes out of guy Arthur Adamson, wrote a book called Physical Chemistry of Surfaces. It's now in its 6th edition, and his co-author for the 6th edition was Alice Gass. Anybody who know who Alice Gass is? She was actually assistant provost at MIT. She came from Caltech or somewhere, I can't remember where. She's now president of Lehigh University. But in any case, I guess she was probably one of Adamson's students. But in the book, he wrote a whole book, now in its 6th edition, on surfaces and surface chemistry. And if I am going to blow this up a little bit so we can read a little bit better, but it's got tables of different materials and typical surface energies. So if I blow this up and you see water on here, water has at 20 degrees C, room temperature, has a surface energy of 73 dynes per centimeter. Okay? That's also the same units as ergs per square centimeter. Turns out if you do surface energy as a force, it's dynes divided by centimeters. If you divide by another centimeter, you'll get ergs per square centimeter. So it's the surface energy per unit area. But they put it as dyne centimeters, same units. And you can go down through here. All your organic liquids here have got surface energies of less than 100 dynes per centimeter, or ergs per square centimeter. And when you get down here to some of the things that have very low surface energy, like your hydrocarbons, heptane, octane, you're down around 20. Okay? If I come over to the other side here, here's some liquid vapor surface energies. You get to liquid helium, it's got a surface energy that's less than 1 dyne, and so cryogenic gases have very low surface energies, and we'll explain that. You get to metals, and you get some pretty interesting surface energies on the order of 500 or more. You get to salts, and the surface energy is back around 100. You get here to high melting metals, not low melting ones like mercury. You get up to almost 2,000 ergs per square centimeter. Now, and turns out 1,000 ergs per square centimeter is equal to 1 joule per meter squared. So there's 10 to the minus 7 dynes in a Newton, and if you've got 10 to the 4th centimeters in a square centimeters in a square meter, and you've got 10 to the minus 7 ergs per joule, and you go through all this, you'll find that the conversion is 1,000 ergs is equal to a joule. So it turns out metals are somewhere around a joule per square meter, whereas most other things are significantly lower. And why is that? Does anyone know why that is? I mean, metals have, we talked about bond energies before, and we said the primary bonds are like 1 to 3 electron volts per atom. But metals are unique because their bonds are non-localized. Remember the covalent bonds and ionic bonds have a distance of about 1 atom. Okay? They go about 1 atomic distance away. And by 2 atomic distance away, they've really dropped off. This is the average bond energy versus intermolecular distance. This is in nanometers. And by the time for covalent and ionic, by the time I've gotten to 2 angstroms away, I'm way down here. It's somewhere at 1.5 angstroms, I get lots of attraction or by bond energy. But as I decay, as I get further away, basically ionic materials react to the atom next to them. The second nearest neighbor, they don't care so much about. very insular, they're hermits, okay? Covalent bonds are usually the same way. Metallic bonds, on the other hand, have significantly greater distances, several atomic distances away, lower overall energy. It turns out, believe it or not, the area under this curve and the area under that curve are the same. Anybody know why? Because you'd have to do this on a square basis. If you're going out in a cylindrical system, when you go, this would be RDR, or R squared, if you will. So you have to multiply this by RDR. And if you take the area under this curve, it's similar. If this is 1 to 3 electron volts, that's going to be 1 to 3 electron volts, even though it doesn't look like it when you do it in one dimension. Okay? If you did it on an area basis, you'd find it's still primary bonds have about the same energy. Hydrogen bonds and van der Waals bonds actually stretch out further. Okay? But they're much weaker, as it turns out. So anyway, what this means, if we do a model of surface energy, hopefully this might show up, saves me time of drawing this on the board. If I have a bunch of atoms in a crystal, and I will have some unsatisfied bonds here. And those unsatisfied bonds are what lead to surface energy. Surface energy is always positive. It cannot be negative. If surface energy were to go negative, the solid or the liquid would become a gas. Why? If the thing doesn't want to bond, which means the bond between the A atoms and the A atoms is less than being non-bonded, it's going to become a gas, right? Spontaneously. It will vaporize. It turns out, even at the melting point or the vaporization point, there's usually still some positive surface energy, okay? Because you get into entropy effects and things like that. But in fact, surface energy, if the thing didn't want to bond, it wouldn't be a solid, it wouldn't be a condensed phase, okay? It wouldn't be a solid or a liquid. So these unsatisfied bonds represent a higher energy state in the material. Think of this as a thermodynamicist, okay? You're all material scientists here, right? Are you? You're from course 3, right? So if you think of this in terms of thermodynamics, an unsatisfied bond, higher energy state, so surface energy is always positive. And what comes down here, here I got a carbon dioxide molecule, here I got an O2, here I got, what I'm trying to draw is something like a stearate, which has a polar, this is like soap, okay? Has a polar end, so it attaches here, and it has a non-polar thing. So stearate soaps are long little hydrocarbon chains with a polar end, okay? Oleates, stearates, all these things. So in any case, what was I doing with this once? I don't know what I was doing with this. Surface energy is always positive. Oh, I know what I'm doing. I know what I was doing with this. Of course I. So here, for ionic and covalent, the surface energy comes from just the top 2 layers, right? You get more than 2 atom distances away, and that curve for covalent and ionic drops off. For metallic, these free electrons that are non-localized, we can get distances of bond energies, electrons, the number of electrons involved in the surface energy is much greater by a factor of 2 or 3, and therefore they have surface energies that are 2 or 3 times higher. Duh. Okay. I did that in my head. Okay. So now you know something about surfaces and why metals have high surface energies. It turns out it's very valuable that metals have high surface energies because in soldering and brazing, we're going to take advantage of that in order to allow ionic or covalent liquids, which we use as fluxes, to clean the surface. Remember, we got 2, here's my theme again, got 2 things preventing bonding. You've got contamination and you got surface roughness. And I've been talking about cold welding, but what we're going to finally get out of cold welding or pressure welding, which involved ultrasonic and friction and explosive and thermocompression bonding. We're going to get back to thermocompression when we deal with electronic bonding and electronics. But I've got to get rid of my surface contamination, I can do that with a flux. And that flux is usually going to be something like a molten salt, something that has a relatively low surface energy. It's going to go across that surface, it's going to take those oxides and those carbon dioxide and that oil, and it's going to clean that surface. But then I want to interpose a metal, a liquid metal in there, that will now want to thermodynamically displace the lower energy, the lower surface energy, organic or inorganic liquid. So metals like to bond to metals because they have similar bonding types. Their interfacial energy will be lower because they are more satisfied having another metal atom on the surface than having a non-metal atom. So that's actually the third, kind of a third thing about bonding, the strength of bonds and surfaces. Some people, it's not just surface roughness and surface contamination. Some people say similar bonding types. Metal bonds are going to be stronger than metal ceramic bonds, whether it be covalent or ionic, okay? And I'm going to take advantage of that when I go into soldering and brazing, which is what we'll do tomorrow. Tomorrow? Yeah, today's Thursday, that's right. Tomorrow, we'll do soldering and brazing. Okay.